A chaotic system is one that follows the laws of physics, yet produces outcomes that seem unpredictable. That behavior isn't random, but it's highly sensitive to initial condition. Even the smallest difference in the starting value, too small to even measure, can lead to a completely different outcome over time. That's what makes chaotic systems so hard to calculate. You can write perfect equations, but if your input is off by just a fraction, the prediction quickly becomes meaningless. This sensitivity means that long-term forecasting, even with powerful computers, becomes unreliable. It's not a failure of the math, it's a reflection of how complex the systems truly are. We see this in weather. We see it in the motion of a double pendulum. Systems that can seem simple but behave in ways we can't fully predict. That's chaos, and it's everywhere.
The double pendulum is one of the simplest systems in physics and one of the most unpredictable. Two rigid arms connected end to end. Gravity pulls them and momentum drives them, but once you let them swing, the motion quickly becomes chaotic. At first, it may move smoothly, but very quickly it begins to spin, twist, and flip in ways that are nearly impossible to predict. That's because the motion of the second pendulum depends not only on itself, but the constantly changing movement of the first. This is what makes it a chaotic system. Even a tiny change, just a fraction of a degree in the starting angle, or a hair's difference in length, leads to a completely different path. Over time, those small differences grow exponentially. It's not randomness, it's sensitivity, and that's what makes the double pendulum a perfect example of the chaotic systems in physics. You can see in the examples we dropped the double pendulums nearly exactly the same, and they all ended up in very different outcomes. You can see when we overlay them, they start off similar, but then quickly change into very different paths.
The weather is one of the most powerful and unpredictable systems on Earth. It seems familiar: wind, clouds, sun, and rain. But beneath it all is a delicate balance of forces, consistently shifting, consistently interacting. It begins with solar energy. The sun heats the Earth, warming oceans, land, and air at different rates. This creates temperature differences, and those temperature differences in air in motion, wind is born from imbalance. Wind carries moisture gathered through evaporation from oceans, lakes, and plants. That moisture becomes clouds and eventually rain, but how much rain, where it falls, and when it depends on a dozen of other factors. Air pressure, humidity, wind speed, cloud formation, terrain, altitude, ocean currents. They all influence one another. Changing one just slightly and the outcome can shift entirely. That's the nature of chaotic systems. Even when we understand the rules, tiny changes in the beginning can lead to completely different results over time. We try to model it. We measure the atmosphere with satellites, balloons, and radar. We simulate it with powerful computers, and for the short term, we do well. But over time, small uncertainties grow. A gust of wind here, a patch of warm ocean there, and suddenly a storm appears where none was expected. A cold front slows down, a hurricane changes course. It's not because the system is random, it's because it's too sensitive, too complex, and constantly changing. That's why the weather for all our science remains a chaotic system, predictable for a moment, but never for long term. Chaotic systems follow the laws of physics, but even the smallest change in the starting conditions can lead to vastly different outcomes. The double pendulum shows us clearly one small shift and its motion becomes completely different. The weather behaves the same way. Tiny changes in temperature, wind, or moisture can reshape an entire forecast. These systems aren't random, just extremely sensitive and complex. In both sky and steel, chaos reminds us small beginnings can lead to unpredictable ends.